Imagine standing next to something so loud that your body doesn't hear it. It simply stops existing. Not gradually, not painfully, but instantly. The pressure wave arrives and you transition from organized matter to dispersed atoms before a single nerve impulse can fire, before pain registers, before your brain processes the word sound. Now imagine that this isn't happening on Earth during some catastrophic explosion, but in the depths of space where sound shouldn't exist at all. And yet, if it could, this is what the universe would sound like at its most violent. Hello, and welcome to the Sleepy Astronomer. Tonight we're going to explore a paradox that sits at the intersection of physics and imagination, the loudest sound the universe has ever produced, in a cosmos where sound cannot travel. We'll journey from the absolute silence of space to a hypothetical universe where cosmic violence could be heard, and we'll discover why that silence we take for granted is actually one of the things keeping us alive. Because there's a particular event, recorded by our instruments in 2008, that released more energy in 23 minutes than our sun will emit across its entire 10 billion year lifetime. And if that energy could have been converted into sound, nothing within a light year would have survived. If you're settling in for the first time, welcome to these gentle explorations of cosmic mysteries. And if you've drifted with me before through deep time and distant stars, it's wonderful to have you back for another journey. If these peaceful wanderings through space and time bring you comfort or curiosity, don't forget to subscribe so you don't miss the next journey into the cosmos. And if this paradox intrigues you, how the universe's greatest violence unfolds in perfect silence, a gentle light helps others find their way to these nocturnal wonderings about the cosmos. Here's what makes this story so compelling. Space isn't just quiet, it's fundamentally silent. Sound requires matter to vibrate, molecules close enough to bump into each other and pass along their trembling. Space has so little matter, roughly 1 atom per cubic centimetre between the stars, that sound waves simply cannot exist. When a star explodes with the force of 1 billion nuclear weapons, when black holes collide and merge, when galaxies tear each other apart gravitationally, it all happens without a whisper. The most violent events imaginable occur in absolute, perfect quiet. And yet, we know exactly how much energy these events release. We can measure it, quantify it, express it in watts and joules. We can calculate what would happen if, just hypothetically, space were filled with a medium thin enough not to disrupt the cosmos, but dense enough to carry sound. We can translate electromagnetic radiation into acoustic pressure. We can determine how loud 12 billion light years of cosmic violence would be if it could make noise. The answer is terrifying in its precision. So, take a deep breath. Let your mind settle into the quiet around you, and get comfortable, because tonight we're exploring the loudest sound that could ever exist, and why the fact that you'll never hear it is one of the greatest blessings the universe provides. The universe is screaming. We just can't hear it, and that's exactly how it should be. Before we can understand why a hypothetical sound in space might kill you instantly, we should probably understand why space doesn't make sound in the first place, which means we need to talk about what sound actually is. And I promise this will be more interesting than it sounds, though admittedly that's setting the bar quite low. Sound is not, as it turns out, a thing unto itself. It's more of a process, a relay race played by molecules. When you clap your hands together, you compress the air between your palms. Those compressed air molecules, finding themselves suddenly and rudely shoved closer to their neighbours, push outward. They bump into the molecules around them, which bump into their neighbours, which bump into theirs. A wave of compression travels outward through the air, followed by a wave of rarefaction, the fancy term for less compressed, and the pattern repeats. Compression, rarefaction, compression, rarefaction. Like a cosmic game of telephone, except the message is just something vibrated over here. This is what sound is. Matter trembling, passing its shiver along. The speed at which this shiver travels depends entirely on the medium carrying it. In Earth's atmosphere at sea level, sound moves at about 343 meters per second, fast enough that nearby sounds feel instantaneous, but slow enough that you can watch lightning strike and then count the seconds until thunder arrives. Each second represents roughly a kilometer of distance, a useful bit of information if you're trying to determine whether that storm is getting closer or whether you should stop standing in an open field like a human lightning rod. Different materials carry sound at different speeds. Water, being denser than air, carries sound faster, about 1,500 meters per second. Steel carries it at roughly 5,000 meters per second. The pattern is clear. The more tightly packed the molecules, the more efficiently they can transfer vibrations to their neighbors. It's easier to play molecular telephone when everyone's standing close together. This is the crucial bit for understanding space. Sound needs matter. Not just any amount of matter, but matter in sufficient density that molecules are close enough to regularly bump into each other. The medium doesn't have to be dense by everyday standards. Air at sea level is mostly empty space, with molecules separated by distances many times their own diameter. But there are still roughly 10 billion molecules per cubic centimetre. That's 10 to the power of 19 if you're keeping count. More than enough for sound waves to propagate happily. Now consider space, specifically the space between stars, what astronomers rather optimistically call the interstellar medium, as though it's actually a medium in any meaningful sense. The density out there averages about 1 atom per cubic centimetre. 1 atom? Not 1 million. Not 1,000. 1. A single hydrogen atom drifting alone in a volume the size of a sugar cube, probably wondering where everyone went. Where Earth's atmosphere contains 10 billion molecules per cubic centimetre, interstellar space contains 1. If you tried to calculate the ratio, you'd get a number so large it would qualify for its own zip code. The interstellar medium is roughly 10 trillion billion times less dense than the air you're breathing, which means calling it a medium is generous to the point of comedy. At this density, the concept of a sound wave breaks down completely. For sound to propagate, molecules need to collide frequently enough to pass along their energy. But when you've only got 1 atom per cubic centimetre, the average distance between collisions is, well, enormous. An atom might drift for thousands of kilometres before encountering another atom. And when it finally does, there's no guarantee that collision will be in the right direction to continue any sort of wave pattern. It's like trying to create waves in a swimming pool that contains exactly 3 water molecules. You can move 1 molecule, certainly. You might even get it to bump into the second one eventually. But you're not going to create the rhythmic pattern of compression and rarefaction that constitutes a wave. You're just going to have a few molecules drifting around independently, wondering why they're in such a large, empty pool. This is why space is silent. Not because there's no matter at all, but because there's so little matter that sound simply cannot exist as a phenomenon. The universe has failed to meet the minimum requirements for acoustic waves. Now, some regions of space are denser than average. Inside nebulae, those beautiful clouds of gas and dust that show up in telescope images looking like cosmic tie-dye, the density might reach 1,000 or even 10,000 atoms per cubic centimetre. This is dense by astronomical standards. dense enough that these clouds can collapse under their own gravity to form stars, dense enough to glow when nearby hot stars ionize them, dense enough to make astronomers excited about dense molecular clouds. But even at these higher densities, space is still nowhere near dense enough for traditional sound waves. 1,000 atoms per cubic centimetre sounds impressive until you remember that Earth's atmosphere has 10 billion per cubic centimetre. Even the densest nebulae are still about 10 trillion times thinner than the air you're breathing. They're vacuum by any terrestrial standard. Extremely high-quality vacuum, the kind you'd need expensive equipment to recreate in a laboratory. Which means that even in the densest regions of interstellar space, the cosmic equivalents of thick fog, sound still can't propagate. The molecules are too far apart, the collisions too infrequent, the medium too tenuous. Space is not just quiet. It's fundamentally, inescapably, perfectly silent. Let's pause here for a moment to appreciate what this means for cosmic violence, because the universe is actually quite violent. Stars explode regularly, black holes devour matter, galaxies collide, neutron stars spiral into each other and merge in cataclysmic displays of gravitational waves and gamma rays. These events release energy that would, in Earth's atmosphere, create sounds loud enough to rupture eardrums halfway across a continent. But in space, they make no sound at all. When a supernova explodes, when a star releases more energy in a few seconds than our sun will emit across its entire 10 billion year lifetime, it does so in perfect silence. Not muffled silence, not distant silence, but absolute acoustic nothingness. The explosion creates a shock wave of matter travelling outward at thousands of kilometres per second, glowing with heat and radiation and magnetic chaos. But it makes no sound. There's nothing to vibrate, no medium to carry acoustic waves, no possibility of the compressions and rarefactions that constitute sound. If you could somehow survive near a supernova, you couldn't, but let's pretend. You would see blinding light. You would feel intense radiation cooking you at the molecular level. You would detect the magnetic fields if you had appropriate instruments. And then you would be vaporized by the approaching wall of stellar debris. But through all of this, you would hear absolutely nothing. The universe's greatest explosion would unfold in silence. This seems wrong, doesn't it? Our brains expect violence to be loud. We've evolved in an environment where dangerous things make noise. Thunder warns of lightning. Predators rustle through grass. Avalanches roar. Our entire auditory system exists to detect threats and opportunities through sound. We're wired to associate catastrophe with noise. But the universe doesn't care about our expectations. Out there, beyond our atmosphere, violence is silent. The most energetic events we know of, gamma-ray bursts, neutron star collisions, black holes shredding stars, all occur without a whisper. The cosmos is playing out the most spectacular destruction on the grandest possible scale, and it's all happening on mute. There's something almost eerie about this. Space feels like it should roar with the accumulated violence of billions of years of stellar death and cosmic catastrophe. Instead, it's quieter than the quietest room you've ever been in, quieter than a sealed chamber, quieter than deep underground. It's the quietest place that exists, not because violence is absent, but because the mechanism for sound simply isn't there. This is the universe we live in. Silent by default, violent without sound, a cosmic pantomime where we see the explosions but never hear them. But what if it weren't? What if space contained a medium, not dense enough to disrupt orbits or scatter starlight significantly, but dense enough to carry sound? Let's say 1 million atoms per cubic centimetre, still 1 million times less dense than Earth's atmosphere. Still vacuum by any terrestrial definition, but dense enough that atoms would be close enough to collide regularly, to pass along vibrations, to form the compressions and rarefactions that constitute acoustic waves. This is the universe we're going to imagine. Not because it exists, it doesn't, but because exploring this hypothetical will teach us something valuable about both sound and cosmic violence. We're going to take the actual physics of real events that happened, that we detected and measured, and translate them into a universe where sound can travel. And when we do, we're going to discover something remarkable. The universe at its most violent would be completely, horrifyingly, instantly lethal in ways that pure radiation never could achieve. So, let's build our hypothetical universe. Carefully, with the understanding that we're changing exactly one variable and keeping everything else the same, which is easier said than done, because the universe is an interconnected system where changing one thing often cascades into changing everything else. But we'll be gentle with our modifications. The key parameter is density. We need space to be filled with something, a medium thin enough not to disrupt the fundamental workings of the cosmos, but dense enough to carry sound. Let's settle on 1 million atoms per cubic centimetre. This might sound like a lot, but remember, Earth's atmosphere has 10 billion atoms per cubic centimetre. Our hypothetical medium is still 1,000,000 times thinner than air. It's vacuum by any terrestrial standard, but it's 1,000 times denser than typical interstellar space, which means, crucially, atoms are now close enough to bump into each other regularly. In this medium, sound would travel at roughly 300 meters per second, slightly slower than in Earth's atmosphere, but the same order of magnitude. The physics would be familiar. Compression waves would propagate predictably, following the same rules we understand from terrestrial acoustics. Distance would matter. Frequency would matter. Loudness would scale in recognizable ways. The main difference would be scale, where sound on Earth travels a few kilometers before dissipating into inaudibility. Sound in our hypothetical space could travel for light years before finally fading. Acoustic waves could cross the distances between stars, carrying the signature of whatever violence created them, arriving years or decades after the event itself. There's something almost peaceful about imagining this, isn't there? The universe gaining a new dimension of sensation, a way of experiencing cosmic events that we currently lack, but we should be careful not to romanticize it too much, because what we're actually describing is a universe where mechanical violence can propagate across interstellar distances, where every energetic event doesn't just emit light and radiation, but also sends pressure waves rippling through space, where the cosmos becomes essentially a very large and very violent bell that never stops ringing. Let's start with the familiar and work our way up to the catastrophic. Ordinary stars like our Sun, would hum constantly. The nuclear fusion occurring in their cores, the convection currents churning through their outer layers, the turbulence of their photospheres, all of this activity would generate pressure variations in the surrounding medium. The result would be a continuous drone, a deep background noise that would fill any solar system in our hypothetical universe. If you could somehow stand on Mercury, ignoring the lethal heat and radiation, which admittedly is a lot to ignore, you would hear the Sun. A low, rumbling drone punctuated by occasional sharper sounds when flares erupted or prominences erupted from the surface. The intensity would probably be around 100 to 120 decibels, loud enough to be uncomfortable over long periods, comparable to standing near a busy highway or inside a factory, not immediately dangerous but definitely not conducive to peaceful contemplation of the cosmos. Different types of stars would produce different sounds. Massive hot stars, blue giants burning through their fuel at prodigious rates, would roar with higher frequency components. Cooler red dwarfs would emit deeper, more bass-heavy drones. Variable stars, those that pulse or fluctuate in brightness, would create rhythmic patterns, acoustic signatures that would repeat on timescales of hours or days. The universe would have a soundscape, a cosmic symphony playing out across every wavelength the human ear could detect, and many it couldn't. Solar flares would add percussion to this background hum. When magnetic field lines on a star's surface snap and reconnect, releasing energy equivalent to millions of nuclear bombs in a matter of minutes, the result would be an acoustic crack. Sharp, powerful, carrying across the solar system at the speed of sound in our medium. If you were orbiting a star prone to frequent flares, you'd experience regular booms rolling across space, each one carrying enough energy to vibrate your spacecraft, assuming you had a spacecraft, which is optimistic given that building spacecraft in an acoustically violent universe seems like it would present certain engineering challenges. Black holes would contribute their own sounds, not from the event horizon itself. Nothing escapes from beyond that point, acoustic or otherwise, but from the accretion disk, that swirling maelstrom of matter spiraling inward, heating to millions of degrees through friction, radiating energy across the electromagnetic spectrum. In our sound-carrying universe, this would include acoustic energy, deep, resonant bass notes extending far into the infrasonic range, too low for human ears to hear as distinct sounds, but powerful enough to feel as vibrations. The universe's largest black holes, supermassive monsters at the centers of galaxies, would emit sounds so deep and so powerful they'd shake entire star systems, a constant bass rumble that would never cease. There's actually something real underlying this, which is worth mentioning. In 2003, NASA astronomers discovered that the supermassive black hole at the center of the Perseus galaxy cluster was producing pressure waves in the extremely tenuous gas surrounding it. They translated these pressure waves into sound, though it required shifting the frequency up 57 octaves to bring it into human hearing range. The result was a deep, somewhat ominous tone that the internet immediately labeled the sound of a black hole, which isn't quite accurate but makes for good headlines. In our hypothetical universe, you wouldn't need to shift frequencies. The sound would be there, audible, constant, and absolutely unavoidable if you lived anywhere near a feeding black hole. Now let's move up the violence scale. Novae, where white dwarf stars pull matter from companion stars and ignite it in thermonuclear explosions, would produce sharp acoustic pulses, brief but intense. If you were in the same solar system when a nova erupted, you'd hear a bang hours after seeing the flash, the sound wave having travelled at 300 meters per second, while the light travelled at 300,000 kilometers per second. The intensity would be dangerous, possibly lethal if you were close enough. But novae are relatively modest as cosmic explosions go. They're the firecrackers of the universe, impressive up close, negligible at distance. Supernovae are where things start to get genuinely frightening. A typical Type II supernova, where a massive star exhausts its fuel and collapses, releases about 10 to the power of 44 joules of energy. For context, that's roughly equivalent to all the energy our Sun will emit across its entire 10 billion year lifetime, compressed into a few seconds. In electromagnetic form, this energy is already terrifying. In acoustic form, in our hypothetical universe, it would be apocalyptic. At the point of explosion, the acoustic intensity would be beyond any meaningful scale. The stellar material itself, hundreds of thousands of times the mass of Earth, would be accelerated to a significant fraction of light speed. When this matter ploughed into our sound-carrying medium, it would create a shockwave of compression so extreme that calling it sound feels inadequate. Nearby planets would be destroyed, not by radiation, but by pure mechanical pressure. The acoustic wave would propagate outward for dozens or hundreds of light years before finally dissipating into undetectability. If a supernova occurred within, say, 10 light-years of Earth in our hypothetical universe, we would detect the light first, seeing the star explode, watching it briefly outshine its entire galaxy. Then, years later, the sound would arrive. We'd have warning. Time to prepare, though. Preparing for an acoustic wave carrying the energy of an exploding star is, well, it's unclear what preparation would even look like. Build underground, go to the opposite side of the planet and hope the Earth itself absorbs some of the energy? These are not encouraging options. The sound intensity when it arrived would depend on distance, but we're talking about levels well above 300 decibels, the threshold at which pressure waves begin to simply disintegrate matter. Earth's atmosphere would be stripped away or at least severely disrupted. The surface would experience heating from compression. The acoustic energy alone would be sufficient to cause mass extinction, even before accounting for the radiation effects we'd also be experiencing from the original explosion. But supernovae, as violent as they are, aren't the peak. That distinction belongs to a phenomenon that combines extreme energy with extreme concentration, producing the most intense events we know of in the universe, gamma-ray bursts. These occur in two main varieties, both involving stellar collapse and the formation of black holes. Long-duration bursts, lasting more than 2 seconds, are associated with hypernovae, the deaths of extremely massive stars. Short-duration bursts, under 2 seconds, result from neutron star mergers. Both scenarios create the same basic result: collapsing matter, a forming black hole, and jets of material and energy shooting outward at relativistic speeds. These jets are the key. Unlike supernovae, which release energy relatively uniformly in all directions, gamma-ray bursts concentrate their energy into narrow beams with opening angles of just a few degrees. It's the difference between a light bulb and a laser pointer. The total energy might be comparable, but the intensity in the beam is vastly higher. The most powerful gamma-ray bursts release upward of 10 to the power of 47 joules, 1,000 times more than a typical supernova. And because this energy is focused into jets rather than spread across a sphere, the intensity in the jet's path is even higher. These are the most energetic single events we know of. Nothing else comes close. In our silent universe, gamma-ray bursts are already terrifying. They're jets of gamma radiation traveling at 99.9% of light speed, carrying enough energy to sterilize planets across multiple star systems if the beam happens to point their way. But they're directional, which means most of them miss us, and they're brief, seconds to minutes, which limits the total dose of radiation. In a sound-carrying universe, gamma-ray bursts would produce acoustic shock waves of unimaginable power. The relativistic jets would plough into our hypothetical medium at velocities approaching the speed of light, roughly 3 million times faster than the speed of sound in that medium. The result would be the mother of all sonic booms, a pressure wave so extreme it would make supernovae seem gentle by comparison. At the point of origin, the acoustic power output would exceed 10 to the power of 38 watts. That's more continuous power than most supernovae emit electromagnetically. Sustained for minutes, creating a pressure wave that would propagate outward at 300 meters per second, carrying enough energy to destroy anything in its path for light years in every direction. This is the loudest sound the universe can produce, not theoretically, not extrapolating beyond observed phenomena, but based on actual events we've detected and measured. Gamma-ray bursts happen. They release these energies. We know they do because we've seen them. And in 2008, we detected one that set the record. An event so energetic it redefined our understanding of what's possible in the universe. An explosion that occurred over 12 billion light-years away, so far that its light had been travelling toward Earth for most of the age of the universe, and was still bright enough to temporarily blind our instruments. This is the event we're going to explore. This is the sound that would instantly kill you if sound could travel through space. This is the monster lurking in our hypothetical universe, the acoustic apocalypse that makes everything else seem quiet by comparison. But before we can understand how loud it would be, we need to meet it properly. We need to understand what created it, when it occurred, and why astronomers were so shocked when they analysed its energy output. Let's introduce the beast. On September 16, 2008, at 0012 UTC, NASA's Fermi Gamma Ray Space Telescope detected something extraordinary. Though to be fair, detecting extraordinary things was literally its job description. The telescope had been launched specifically to observe gamma-ray bursts and other high-energy phenomena. So, when its instruments began recording a surge of gamma rays from a point in the constellation Carina, the initial response was probably something along the lines of good, it's working as intended. But as data streamed in and astronomers began their analysis, the tone likely shifted. Because this wasn't just another gamma-ray burst, this was the gamma-ray burst. The one that would make all previous records look modest. The one that would force scientists to recalibrate their sense of what's possible when stars die. The burst lasted 23 minutes, which is, by gamma-ray burst standards, quite long. Most are done in seconds. For 23 minutes, Fermi's detectors recorded high-energy photons arriving from a single point in the southern sky. And when astronomers calculated the total energy output, accounting for the burst distance and the expansion of the universe, the number they got was absurd. 8,800 times more energy than our Sun has emitted across its entire 4.6 billion-year lifetime, all released in 23 minutes. Let's sit with that for a moment. Our Sun has been burning steadily for billions of years. It will continue burning for billions more. Every second it converts about 4 million tons of matter into energy through nuclear fusion. It's been doing this for so long that it's already converted a significant fraction of Jupiter's mass into light and heat. The total energy output over its lifetime is a number so large it requires scientific notation just to write down. And this gamma-ray burst, this single event, this brief violent death of a star 12 billion light-years away, exceeded that by a factor of 8,800. The burst was designated GRB 080916C. The naming convention is wonderfully unromantic, GRB for gamma-ray burst, followed by the date of detection in year-month-day format, then a letter indicating it was the third burst detected that day. C. As though this were just another item on a list, a bureaucratic designation for cosmic violence that defies comprehension. Though to be fair, what would be an appropriate name? Astronomers could hardly call it the absolutely terrifying death scream of an ancient star every time they referenced it in papers. GRB 080916C is concise, informative, and has the advantage of not giving existential dread to graduate students who have to type it repeatedly. The burst occurred 12.2 billion light-years away, which means we were observing an event that happened when the universe was only about 10% of its current age. The light and gamma rays had been travelling toward Earth for most of cosmic history, crossing an expanding universe, finally reaching our detectors in 2008. We were seeing ancient violence, a star that died when the cosmos was still young, when galaxies were still assembling, when the first generation of stars was just beginning to enrich space with heavy elements. Despite that immense distance, despite the fact that the signal had been diluted by spreading across a sphere with a radius of billions of light years, it was still bright enough to temporarily blind several of Fermi's detectors. If this burst had occurred in our galaxy, say 10,000 light-years away instead of 12 billion, the radiation would have been intense enough to strip Earth's ozone layer and trigger a mass extinction. At 1,000 light-years, it would have sterilized our planet's surface entirely. Fortunately, gamma-ray bursts are directional. The energy is focused into narrow jets, typically with opening angles of just a few degrees. This means we only detect them when one of those jets happens to point directly at Earth. For every burst we see, there are likely hundreds or thousands occurring that we never detect because their jets point elsewhere. It's cosmic Russian roulette, and mostly we're not in the line of fire. GRB 080916's jet was pointed right at us. We received the full force of its focused energy, diminished only by distance and the expansion of space itself. Lucky us. So what created this violence? What sequence of events leads to a single star releasing 8,800 suns worth of energy in 23 minutes? The answer involves a star dying in the most dramatic way physics allows. Gamma-ray bursts come in two main flavors, distinguished primarily by how long they last. Short bursts under 2 seconds are typically produced when two neutron stars spiral into each other and merge, or when a neutron star merges with a black hole. These are violent enough in their own right, but they're not the record holders. Long bursts, anything over 2 seconds, are associated with hypernovae. These are not your standard supernovae, which are already impressively destructive. Hypernovae are what happens when truly massive stars die. Objects with initial masses perhaps 30 to 100 times that of our Sun. Stars so massive that when they finally exhaust their nuclear fuel, the collapse is fast, complete, and extraordinarily energetic. GRB 080916c was a long burst, which means it almost certainly came from a hypernova. Here's how the process unfolds as best we understand it. A massive star spends its life in a constant battle between gravity trying to crush it and nuclear fusion pushing outward. For millions of years, fusion wins. The star burns hydrogen into helium, then helium into carbon and oxygen, then progressively heavier elements up the periodic table. Each stage produces less energy and lasts a shorter time. Hydrogen burning might last millions of years. Silicon burning, the final stage before catastrophe, lasts about a day. When the core has been converted to iron, fusion stops. Iron is the end of the line. Fusing iron consumes energy rather than releasing it, so the core can no longer support itself against gravity. And gravity, having waited patiently for millions of years, finally wins. The core collapses in less than a second. Matter that occupied a volume the size of Earth compresses down to a sphere perhaps 20 kilometers across. If the star is massive enough, and for gamma-ray burst progenitors, it definitely is, the collapse doesn't stop at neutron star densities. It continues collapsing into a black hole. But the collapse doesn't happen uniformly. The star's rapid rotation causes matter to collect into an accretion disk around the forming black hole. This disk is extraordinarily hot, billions of degrees, heated by friction and compression as matter spirals inward. Magnetic field lines, frozen into the plasma, spiral inward with the infalling material and become twisted and amplified. The magnetic energy density becomes enormous. Eventually, we're still talking timescales of seconds here, the magnetic fields become so strong and so twisted that they launch jets of matter and energy perpendicular to the accretion disk. These jets bore through the collapsing star like cosmic drill bits, ploughing through thousands of kilometers of stellar material. When they finally break free into space, they're traveling at more than 99.9% of the speed of light. These relativistic jets carry matter, electrons, positrons, ions, all accelerated to extreme energies. They carry electromagnetic radiation, particularly gamma rays, and they carry magnetic fields that create complex structures within the jets, regions where charged particles spiral and radiate even more energy. As the jet ploughs into the interstellar medium, even the tenuous hydrogen between stars, it creates a shock wave. This is called the external shock, and it's where most of the gamma-ray emission originates. Particles in the shock front are accelerated to incredible energies, then slow down and radiate that energy as gamma rays. The process is extraordinarily efficient at converting kinetic energy into radiation. A typical gamma-ray burst might release 10 to the power of 44 to 10 to the power of 46 joules in gamma rays. This makes them, for their brief duration, the brightest objects in the universe, more luminous than all the stars in their host galaxy combined. They can be detected across billions of light years. They are, in essence, the universe's way of saying, "Look at this," in the loudest possible voice. GRB 080916. He released approximately 8.8 times 10 to the power of 47 joules. To put that in perspective, since perspective is increasingly difficult at these scales, the Hiroshima atomic bomb released about 6.3 times 10 to the power of 13 joules. The largest nuclear weapon ever detonated, the Soviet Tsar bomber, released about 2.1 times 10 to the power of 17 joules. A typical supernova releases about 10 to the power of 44 joules. Our Sun's total lifetime energy output will be roughly 10 to the power of 44 joules. GRB 080916C released roughly 10,000 times more energy than a supernova, roughly 10,000 times more than our Sun's entire life's work. It did this in 23 minutes. The numbers become so large they start to lose meaning. Our brains aren't equipped to process differences at these scales. The difference between 1,000,000 and 1,000,000,000 is already hard to grasp intuitively. The difference between 10 to the power of 44 and 10 to the power of 47 is the difference between unimaginably large and even more unimaginably large. We can write the numbers, we can calculate with them, but we can't really feel what they mean. Which brings us back to our hypothetical universe, the one where sound can travel, because in our actual silent universe, this energy radiated away as gamma rays, X-rays, and charged particles. It dispersed across space, weakening with distance according to the inverse square law, eventually reaching Earth as a detectable but not dangerous flux of high-energy photons. But in our sound-carrying universe, what would happen when this relativistic jet, travelling at 99.999% of light speed, slammed into our hypothetical medium of 1,000,000 atoms per cubic centimetre? The jet's kinetic energy would begin transferring to the surrounding gas, not gently, not gradually. The jet would compress the gas in front of it to enormous densities, creating a forward-moving shockwave. At relativistic velocities, you're not just moving fast, you're moving so fast that the gas doesn't have time to move out of the way. It piles up, compresses, and heats to millions or billions of degrees. When an object moves faster than the speed of sound in a medium, it creates a sonic boom, a shock wave trailing behind it. The space shuttle re-entering Earth's atmosphere produced such booms. Supersonic jets produce them. But these are gentle compared to what a relativistic jet would create. The jet from GRB 080916C was moving at approximately 99.9999% of the speed of light in our hypothetical medium, where acoustic waves travel at roughly 300 meters per second. The jet's velocity would be about 1 million times faster than the speed of sound. This isn't just supersonic. This isn't even hypersonic. This is relativistic velocity colliding with a medium that can barely comprehend motion at such speeds. The shock front that forms at the interface between the jet and the ambient medium would be a discontinuity in space itself, a razor-thin boundary where density, temperature, and pressure jump by factors of thousands or millions. Behind this leading shock, the jet's energy would continue to dissipate into the medium. Turbulence would develop. Magnetic fields would amplify. Particles would accelerate and collide. Over hours and days, a vast region of space would become energized, glowing with heat and radiation, and, in our hypothetical universe, vibrating with acoustic energy. Now we can start our calculation. Let's assume, conservatively, that about 1% of the jet's kinetic energy converts into acoustic waves in the medium. This is actually quite conservative. Some astrophysical shocks convert much more than this. But even at 1%, we're dealing with roughly 10 to the power of 45 joules of acoustic energy. How loud is 10 to the power of 45 joules? This is where we need to talk about decibels, about pressure waves, about the difference between loud and instantly fatal. But before we build that ladder from whispers to apocalypse, we should appreciate what we've established. We have a real event detected and measured. We have its energy output calculated from observations. We have the physics of how that energy would interact with our hypothetical medium. Everything from here on is just translation, converting electromagnetic radiation into acoustic pressure, calculating intensities at various distances, determining lethal thresholds. The physics is straightforward, if somewhat grim in its implications. Because here's the thing, even in our silent universe, GRB 080916C was terrifying. The gamma radiation alone would have been fatal to any life within thousands of light years if the jet had been pointed in their direction. But gamma radiation is at least fast. It arrives at light speed, giving no warning, but also killing quickly. In a sound-carrying universe, the acoustic shockwave would be slower. It would arrive years after the light, after the radiation, giving plenty of warning. But when it finally reached you, it wouldn't just irradiate you or heat you or disrupt your molecular bonds. It would erase you, convert you from organized matter into expanding plasma, not through any exotic physics, but through pure mechanical pressure. Sound in sufficient quantities stops being sound and becomes something else entirely, a force, a wall of compressed matter moving at 300 meters per second, carrying enough energy density to make nuclear weapons look gentle. And GRB 080916C, if it could produce sound, would be the loudest thing the universe has ever created. Before we can understand how loud GRB 080916C would be as sound, we need to understand the scale we're using to measure loudness, which means we need to talk about decibels, a unit that manages to be both elegant and confusing in roughly equal measure. The decibel is a logarithmic unit. This is important and also the source of most of the confusion. When we use logarithmic scales, we're compressing vast ranges of values into something more manageable. This is necessary because sound intensities in the real world vary by factors of trillions. If we tried to use a linear scale, where each step up represented the same absolute increase in intensity, we'd quickly run out of reasonable numbers to work with. Instead, the decibel scale works like this. Every increase of 10 decibels represents a 10-fold increase in acoustic power. An increase of 20 decibels means 100 times more power. 30 decibels means 1,000 times more power. The progression is exponential, which means small changes in decibel level correspond to enormous changes in actual intensity. This has some counterintuitive consequences. A sound at 90 decibels isn't just slightly louder than a sound at 80 decibels, it's 10 times more intense. The difference between a whisper and a jet engine isn't just very loud versus very quiet, it's a factor of 10 trillion in acoustic power. The scale compresses this into a range of about 150 decibels, which is much easier for our brains to work with. The 0 point of the scale is set at the threshold of human hearing, the faintest sound a healthy young person can detect in ideal conditions. This corresponds to a pressure variation of about 20 micropascals, or roughly 20 millionths of atmospheric pressure. It's an almost imperceptible trembling of air molecules, the lower limit of what our auditory system can resolve from background thermal noise. From there, we build upward. And since we're going to climb all the way from whispers to cosmic violence, we might as well start at the bottom and work our way up systematically. Think of this as a ladder, each rung representing sounds roughly 10 decibels apart, each rung 10 times more intense than the one below it. At 0 decibels, we have silence, or rather, the threshold of detection, the faintest possible sound. At 10 decibels, we're in the realm of rustling leaves or very quiet breathing, sound that's present but requires attention to notice. At 20 decibels, a whisper, quiet conversation in a library, the ambient noise level in a recording studio designed for silence. At 30 decibels, a quiet bedroom at night, assuming you don't live near a highway or have particularly loud neighbours. This is the sound level most people find conducive to sleep, present enough that absolute silence doesn't feel eerie, quiet enough that it doesn't demand attention. At 40 decibels, a quiet library or a residential area at night, background hum from appliances, distant traffic, the general murmur of civilization at rest. At 50 decibels, light rainfall, a quiet office, conversation at a moderate distance. This is where sound starts to become a consistent presence rather than something you might not notice. At 60 decibels, normal conversation at close range. Laughter, a television at moderate volume. This is the acoustic environment most humans spend most of their time in, loud enough to communicate clearly, quiet enough not to be intrusive. At 70 decibels, a busy restaurant, a vacuum cleaner, traffic on a moderately busy street, starting to get into the range where prolonged exposure becomes tiring rather than just background. At 80 decibels, we cross an important threshold. This is approximately the level at which sustained exposure begins to risk hearing damage. A garbage disposal, a blender, an alarm clock at close range all hover around this intensity. OSHA regulations in the United States limit workers to 8 hours of exposure at 85 decibels without hearing protection. It's not immediately dangerous, but it's loud enough that your ears will notice, and over time they'll object. At 90 decibels, a lawnmower, a food blender at full power, a motorcycle passing. Definitely loud. Conversation becomes difficult. If you're exposed to this level regularly without protection, hearing damage accumulates over years or decades. At 100 decibels, a nightclub near the speakers, a power saw, a jackhammer at moderate distance. This is where loud transitions to very loud. The threshold of pain is still higher, but this is definitely uncomfortable for most people. Your ears might ring afterward, a sign that the tiny hair cells in your cochlea have been overstimulated. At 110 decibels, a rock concert at full volume, a car horn at very close range, a chainsaw. Hearing damage can occur with just minutes of exposure. The sound is physically uncomfortable. Most people instinctively move away from sources this loud. At 120 decibels, we reach the threshold of pain for most humans. A thunderclap directly overhead, a siren at arm's length, a jet engine at 100 meters, the stapedius muscle in your middle ear, a tiny muscle that normally helps moderate sound levels, contracts reflexively to protect your inner ear, but it's not enough. At this intensity, sound stops being just loud and starts being physically painful. At 130 decibels, a military jet taking off, a gunshot at close range without hearing protection, immediate risk of permanent hearing damage. The sound is intensely painful. Your entire body can feel the pressure waves, not just your ears, but your chest, your skull. Your internal organs all vibrate at these intensities. At 140 decibels, we're at the threshold of immediate physical injury. A jet engine at 30 meters, a large firework at very close range. Eardrums can rupture. The pain is severe. Nobody willingly exposes themselves to this level without substantial hearing protection. At 150 decibels, inside a jet engine, next to a rocket launch, sound becomes dangerous to all tissues, not just hearing. The pressure variations are strong enough to cause vibrations in the chest cavity, potentially affecting heart rhythm. Internal organs experience pressure changes. This is genuinely hazardous acoustic energy. At 194 decibels, something interesting happens in Earth's atmosphere. This is the theoretical maximum for sound in air at sea level. At this intensity, the peak pressure of the compression wave is about twice atmospheric pressure, while the trough, the low pressure part of the wave, drops to zero. Absolute vacuum. You can't have negative absolute pressure, so the wave becomes discontinuous. It's no longer a smooth sine wave, but a shock wave, a travelling wall of compression followed by vacuum. This is the level at the epicenter of large explosions. The shock wave from a substantial bomb, the acoustic environment immediately around a rocket exhaust. At this point, calling it sound is almost misleading. It's a destructive pressure front that tears, crushes and heats whatever it encounters. But 194 decibels is only the limit in Earth's atmosphere. It's a consequence of atmospheric pressure, not a fundamental limit of physics. In denser media, or in a hypothetical space medium with different baseline pressure, there's no such ceiling. Pressure waves can reach intensities far beyond what's possible in terrestrial air. So let's keep climbing. We're leaving Earth now, entering the realm of hypothetical and cosmic sounds. These measurements are theoretical, calculated from energy density rather than measured directly, because nothing survives at these intensities to place a microphone. At 210 decibels, we're in the range of close proximity nuclear explosions. The 1 megaton bombs tested during the Cold War produced shock waves of this intensity within about a kilometre of ground zero. At this level, the pressure is sufficient to instantly kill any organism through sheer mechanical force, before heat or radiation even become factors. Reinforced concrete structures suffer severe damage. The pressure wave alone, forget about heat, forget about radiation, is lethal. At 250 decibels, we're discussing pressures equivalent to thousands of atmospheres. This is getting into the realm of theoretical cosmic events, perhaps the surface conditions on a neutron star if there were an atmosphere to carry sound, or the shock wave very close to a supernova remnant ploughing through a dense nebula. Matter at these pressures doesn't behave like familiar solids or gases anymore. Everything becomes more fluid, more plastic. Molecular bonds are stressed beyond their normal limits. At 300 decibels, pressure variations exceed the tensile strength of essentially all known materials. Steel would flow like honey. Diamond would shatter or deform. Even the exotic matter you might find in neutron star crust would struggle to maintain structure. This is roughly the acoustic intensity you might experience at the surface of a supernova explosion if sound could propagate through space. Instant, total destruction of any organized matter. At 500 decibels, we're beyond any terrestrial comparison. Pressure variations would be millions of atmospheres. Matter can't maintain molecular bonds at these intensities. You'd have plasma, dissociated atoms, electrons stripped from nuclei by sheer violence. The distinction between matter and pressure waves starts to blur. Is it a sound wave moving through matter, or is the pressure so extreme that it's creating and destroying matter as it goes? At 700 decibels, even atomic structure becomes questionable. The pressure variations are so extreme that electrons might be stripped from atoms not by ionization but by mechanical force. You're approaching energy densities where quantum effects become relevant, where the vacuum itself might be affected. At 1000 decibels, we've entered territory where physics gets truly strange. The energy density in the pressure wave is sufficient to create particle-antiparticle pairs from vacuum fluctuations. Space-time itself might ripple in response to pressure variations this extreme. We're discussing intensities where our normal models of acoustics break down completely, where you'd need relativistic quantum mechanics to describe what's happening. And at 1300 decibels, the acoustic intensity of GRB 080916C at 1 astronomical unit, roughly Earth's distance from the Sun, we've transcended any meaningful definition of sound. This is energy density so extreme it makes supernovae look gentle. Let's calculate this properly. At the source of GRB 080916C, right at the point where the relativistic jet emerges from the collapsing star, the acoustic power output would be approximately 10 to the power of 38 watts. This is continuous power, sustained for hundreds of seconds. It exceeds the electromagnetic luminosity of most supernovae. At 1 astronomical unit from the source, about 150 million kilometers, we can calculate the sound intensity by dividing this power by the surface area of a sphere at that radius. The result is approximately 10 to the power of 20 watts per square meter. Converting this to decibels using the standard formula, 10 times the logarithm of intensity divided by the reference intensity of 10 to the power of negative 12 watts per square meter gives us roughly 1300 decibels. 1300. For context, the pressure variations at this intensity would exceed 10 to the power of 50 pascals. That's 10 to the power of 45 times atmospheric pressure. The pressure at Earth's core, the weight of the entire planet pressing down, is about 360 billion pascals. The pressure in GRB 080916C's acoustic wave at 1 astronomical unit would be trillions of times higher. At this intensity, sound is meaningless as a concept. You wouldn't hear anything because you wouldn't exist long enough for hearing to occur. The pressure wave wouldn't kill you. It would prevent you from ever having been organized matter in the first place. Atoms would be smashed apart into constituent particles. Electrons would be stripped from nuclei. The fundamental forces that hold molecules together would be overwhelmed by the sheer momentum of colliding particles. You wouldn't die. You would simply be disassembled at the subatomic level before any biological or chemical process associated with death could occur. How does this compare to other extreme events? Let's put it in perspective, though perspective becomes increasingly difficult at these scales. Krakatoa, the 1883 volcanic eruption, one of the most violent events in recorded human history, produced sound estimated about 180 decibels at close range. It was heard nearly 5,000 kilometers away. It killed tens of thousands of people through tsunamis and pyroclastic flows. The acoustic intensity was enough to rupture eardrums at substantial distances. Krakatoa released roughly 2 × 10 to the power of 17 joules of energy. GRB 080916C released approximately 10 to the power of 47 joules. That's 10 to the power of 30 times more, a trillion times more energy. The comparison isn't even meaningful. It's like comparing a candle to the sun, except even that understates the difference. The Tunguska event of 1908, where a meteor or comet exploded over Siberia with a force of 10 to 15 megatons, produced acoustic intensity around 300 decibels at ground zero. Trees were flattened for kilometers. The shockwave circled the Earth. At the epicenter, the sound would have been instantly lethal through pressure alone. Tunguska released about 10 to the power of 17 joules. GRB 080916C exceeds this by a factor of 10 to the power of 30. Again, the numbers are so large that comparison loses meaning. The largest nuclear weapon ever detonated, Tsar Bomba, 50 megatons, produced sound around 280 decibels at 1 kilometer distance. At that range, the shockwave would kill instantly through pressure, separate from heat and radiation effects. Tsar Bomba released about 2 × 10 to the power of 17 joules. GRB 080916C released. Well, we've established the pattern. The gulf is incomprehensible. Even comparing to other cosmic events doesn't help much. A typical supernova releasing 10 to the power of 44 joules would produce, in our hypothetical universe, acoustic intensity around 800 to 900 decibels at 1 astronomical unit. Catastrophically loud, lethal at interstellar distances. But GRB 080916C exceeds even this by factors of hundreds or thousands in intensity. Among gamma-ray bursts themselves, GRB 080916C sits at the extreme tail of the distribution. Most gamma-ray bursts release 10 to the power of 44 to 10 to the power of 46 joules. GRB 080916C released 10 to the power of 47, 10 to 1,000 times more energetic than typical. It's not just loud. It's the loudest sound the universe has produced under standard physics, from any observed event, converted into acoustic form. Could anything be louder? Hypothetically, perhaps. If 2 neutron stars merged inside an extremely dense molecular cloud, the acoustic coupling might be more efficient. If a supermassive black hole underwent some catastrophic instability we haven't observed yet, it might release more energy. But among events we know actually occur, among phenomena we've detected and measured, GRB 080916C represents the peak. It is, quite literally, as loud as the universe gets. Let's talk about exactly how far away you'd need to be to survive this cosmic scream, for it to not instantly kill you. This requires defining what we mean by lethal, which is trickier than it might seem. For humans unprotected in the path of a pressure wave, lethality begins surprisingly low on the decibel scale. At around 150 decibels, instantaneous exposure can rupture eardrums, painful and damaging but survivable. At 180 decibels, lung tissue begins to tear. At 194 decibels in Earth's atmosphere, The shockwave can cause fatal internal injuries through ruptured organs, torn blood vessels, and disrupted heart rhythm. But these thresholds apply to pressure waves in dense atmosphere, where the relationship between decibel level and physical damage is well established through unfortunate experience with explosions and industrial accidents. In our hypothetical space medium, which is far thinner, the physics change somewhat. The coupling between acoustic pressure and biological tissue would be less efficient in lower density media, meaning you'd need higher decibel levels to produce the same damage. For our purposes, let's define lethal conservatively, the intensity at which a human body would be disrupted beyond any possibility of survival, even with immediate medical intervention. Not hearing loss, not ruptured organs, but the point where tissue structure fails completely, where you transition from organism to dispersed collection of organic molecules. In Earth's atmosphere, this occurs somewhere above 250 decibels. In our thinner space medium, it would require higher intensities, perhaps 300 to 350 decibels, because each individual molecule carries less momentum. But we're dealing with acoustic intensities far above these thresholds, so the distinction becomes somewhat academic. When you're discussing 1300 decibels at one astronomical unit, the question isn't, will this kill you, but rather, how far away do you need to be before it stops being instantly fatal? This requires understanding how acoustic intensity decreases with distance. Fortunately, the physics is straightforward. In free space with no absorption, and our hypothetical medium is thin enough that absorption is minimal. Intensity follows the inverse square law. Double the distance from the source, and intensity drops by a factor of 4. This is because the same acoustic power is spreading over a sphere of increasing surface area, and surface area grows with the square of the radius. The formula is simple. Intensity equals power divided by 4 pi times radius squared. For GRB 080916C, with an estimated acoustic power output of 10 to the power of 38 watts sustained over hundreds of seconds, we can calculate intensity at any given distance. Let's work outward from the source and identify key thresholds. Think of these as concentric spheres of increasing safety, though safety is a relative term when we're discussing the acoustic environment around an exploding star. At the source itself, the point where the relativistic jet emerges from the collapsing hypernova, the concept of sound intensity becomes meaningless. This is the interior of an exploding star, where matter exists as plasma at billions of degrees, where densities exceed those in atomic nuclei, where the distinction between matter and energy blurs. Nothing survives here. Not rocks, not exotic materials, not hypothetical structures made of neutronium. The conditions are so extreme that atoms cannot exist in any organized form. Moving outward to one astronomical unit, roughly 150 million kilometers, Earth's distance from the Sun, we've already calculated the intensity at approximately 1300 decibels. At this range, pressure variations would exceed 10 to the power of 50 pascals. For comparison, the pressure at Earth's core is about 360 billion pascals, the weight of the entire planet pressing inward. The acoustic pressure at 1 AU from GRB 080916C would be trillions of times higher. Matter cannot exist in any organized form under these conditions. Atoms would be disassembled into constituent particles before molecular bonds could even be considered. The pressure wave doesn't kill you in any biological sense. It prevents you from being organized matter in the first place. This is destruction at a fundamental level, below chemistry, below biology, at the realm of particle physics. This zone of total obliteration extends to roughly 100 astronomical units, about where the Kuiper belt is in our solar system, well beyond Pluto's orbit at 30 AU. Throughout this entire region, nothing survives. Planets would be vaporized instantly, not melted, not shattered, but converted directly to expanding plasma. Rocky worlds would cease to exist as coherent objects within seconds of the pressure wave's arrival. Iron-nickel asteroids, the densest natural objects in our solar system, would be heated to millions of degrees through compression alone and dispersed into clouds of metallic vapor. Any hypothetical life in this zone would die so quickly that death seems like the wrong word. There would be no sequence of biological failure, no cascade of cellular damage, no brief moment of awareness. The pressure wave would arrive at the speed of sound, 300 meters per second in our medium, and organized matter would simply cease to exist. One moment, structure. The next moment, plasma. No transition, no middle ground. From 100 to 1,000 astronomical units, we're in what might optimistically be called the rapid destruction zone. Sound intensity here drops to 500 to 700 decibels, still horrifically violent, still instantly lethal to anything resembling life, but at least matter can briefly persist as matter before being destroyed. A rocky planet in this zone would experience a sequence of events, albeit a very brief one. The leading edge of the pressure wave would arrive, heating the atmosphere, if present, to tens of thousands of degrees and accelerating it to escape velocity. Microseconds later, the surface would begin to melt under the combination of compression heating and direct acoustic pressure. The molten surface would then vaporize, and the pressure wave would penetrate into the crust, creating stress patterns that fracture the planet into large fragments. The whole process would take seconds. What was once a coherent world would become an expanding debris field of molten rock and vaporized minerals. Any life would be extinct not through radiation or heat alone, but through the sheer mechanical violence of the planet tearing itself apart. There would be no time for evacuation, no possibility of shelter. Underground bunkers would offer no protection when the entire planet is fragmenting. The acoustic energy would propagate through solid rock more efficiently than through atmosphere, making deep shelter actively counterproductive. From 1,000 to 10,000 astronomical units, roughly 0.15 light-years, we reach the surface destruction zone. Intensity here is 300 to 400 decibels. This is merely catastrophic rather than existentially obliterating, which represents meaningful progress in survivability, relatively speaking. A planet with an atmosphere would lose it. The acoustic pressure wave would compress the atmosphere on arrival, heating it to thousands of degrees, then allow it to expand explosively. Some fraction of atmospheric gases would accelerate beyond escape velocity and be lost to space permanently. Surface structures would be destroyed, mountains leveled by pressure and seismic activity, oceans vaporized or at least heated to boiling, crusts fractured by the acoustic energy propagating through the rocky interior. But, and this is important, the planet as a coherent body might survive. After the shock wave passed, after the acoustic energy dissipated, you'd be left with an airless, sterilized world with its surface melted and reformed, recognizable as a planet rather than a debris field, still orbiting its star, though possibly with a perturbed orbit from the momentum transfer. Any surface life would be extinct. The acoustic wave itself would be lethal. 300 decibels is well above the threshold for instant tissue disruption. But even organisms sheltered deep underground would die as the planet's crust heated from acoustic energy absorption and shook itself apart from pressure-induced seismicity. There's no depth that provides safety when the entire world is experiencing coordinated mechanical violence. However, and this is where survival enters the discussion as more than a purely theoretical concept, life in deep subsurface oceans might persist. If a planet had liquid water kilometers below the surface, insulated by rock and ice, that water might absorb enough acoustic energy to heat significantly without boiling. Single-celled organisms adapted to extreme conditions might survive the heating and pressure changes. Not comfortably, not without significant die-off, but survive in the sense that some viable population remains after the shockwave passes. This is survival in the most technical sense. The biosphere would be devastated. The planet would be rendered uninhabitable to anything more complex than extremophile bacteria. But life, in some form, might persist. From 10,000 to 100,000 astronomical units, about 1.5 light-years, were in the atmospheric disruption zone. Sound intensity here is 200 to 250 decibels, roughly equivalent to being very close to nuclear explosions. Still lethal to unprotected organisms, still capable of causing catastrophic damage, but no longer automatically fatal to all life on a planet. The acoustic pressure wave would compress atmospheres significantly on arrival, creating global heating events. Some atmospheric loss would occur as the hottest gases reached escape velocity. Weather patterns would be violently disrupted. Imagine every atmospheric circulation pattern simultaneously intensified by factors of hundreds or thousands. Hurricanes, tornadoes, thunderstorms of intensity Earth has never experienced. Surface life would face severe challenges. The heat pulse alone might be fatal to most organisms. The pressure changes would be lethal to anything with air-filled cavities, lungs, swim bladders, any organ that relies on maintaining pressure differentials. Large animals would likely die from acoustic trauma and heat stress. But life could survive. Deep ocean organisms would be insulated by water. Underground life would be protected by kilometers of rock. Even some surface life, particularly simple organisms like bacteria, which have no complex structures to rupture, might survive in sheltered locations. The planet would remain habitable in principle, though it would take millions of years for complex ecosystems to recover from the disruption. Beyond 100,000 astronomical units, roughly 1.5 light-years, we finally reach intensities below 200 decibels. This is still violently loud by any terrestrial standard, comparable to being near rocket launches or military explosions, but it's no longer instantly lethal to all organisms. A planet at this distance would experience what amounts to a very loud, very long thunderclap. The acoustic pressure wave would arrive, creating a pulse that would be audible if the planet had organisms with ears, as a deep, resonant boom lasting minutes or hours as the wavefront passed. The atmosphere would experience heating and turbulence. Weather would be disrupted. There might be induced seismic activity from the acoustic energy coupling into the planetary crust. But the planet would remain habitable. Atmospheres would stay bound. Oceans would remain liquid. Life would continue, though probably with significant mortality among organisms at the surface during the peak of the acoustic pulse. After the wave passed, the planet would recover relatively quickly, within years or decades rather than millions of years. The lethal radius for complex life then extends to approximately 1 to 1.5 light-years from the source. Anything within this radius would face extinction-level acoustic trauma in our hypothetical sound-carrying universe. Beyond this radius, survival becomes increasingly probable, though not necessarily pleasant. Let's put this in context of familiar astronomical distances. Our solar system, measured to the edge of the Kuiper belt, extends to about 50 astronomical units. The Oort cloud, that theoretical shell of icy bodies surrounding the Sun, might extend to 100,000 astronomical units, roughly 1.5 light-years. GRB 080916C's lethal radius would encompass not just one solar system, but dozens of nearby solar systems. If such an event occurred at the Sun's position, the acoustic shockwave would be instantly lethal to life on every planet, orbiting every star within 1.5 light-years. In our actual solar neighborhood, where stars are separated by a few light-years on average, this would mean sterilizing multiple star systems simultaneously. Not through radiation, though that would also be devastating, but through pure mechanical acoustic violence. In denser stellar environments, globular clusters where stars are separated by light weeks rather than light years, a single gamma-ray burst in a sound-carrying universe could render thousands of star systems uninhabitable. The acoustic catastrophe would propagate through the cluster like a wave of mechanical death, reaching system after system, overwhelming any protective measures organisms might have evolved. This raises an interesting question about the Fermi paradox. In our silent universe, gamma-ray bursts are already concerning. The gamma radiation from a nearby burst could trigger mass extinctions, but the lethal radius for gamma rays is smaller, perhaps 0.1 light-years for complete sterilization. In a sound-carrying universe, gamma-ray bursts would be an order of magnitude more dangerous. Their lethal radius would be 10 times larger, meaning the affected volume would be 1,000 times greater. Intelligent life attempting to develop in such a universe would face an additional existential threat. Not just the radiation from nearby gamma-ray bursts, which arrives at light speed without warning, but also acoustic shock waves that arrive years later. Even civilizations that survive the initial radiation by being just outside the gamma-ray lethal radius might be destroyed when the acoustic wave arrived years or decades later, traveling at the much slower speed of sound. But we're speculating now, building hypotheticals on top of hypotheticals. Let's return to our specific case. GRB 080916C occurred 12.2 billion light-years away. In our hypothetical sound-carrying universe, its acoustic shock wave would have propagated outward at roughly 300 meters per second, about 1/1,000,000th the speed of light. After 12.2 billion years, that shock wave would have traveled approximately 3.7 million light-years. This means it would have crossed intergalactic space, possibly reached neighboring galaxies, and then, crucially, dissipated into undetectability long before approaching our location. Because acoustic waves, unlike electromagnetic radiation, lose energy to the medium they travel through, each compression heats the gas slightly. Each rarefaction allows cooling. Over millions of years and light-years of distance, even the most intense acoustic wave gradually transfers its energy into thermal motion and eventually fades into the background noise of the universe. By the time GRB 080916C's hypothetical acoustic wave reached us, if it even propagated that far, which is doubtful, it would be undetectable. A slight imperceptible warming of the interstellar medium, indistinguishable from random thermal fluctuations. We are safe from this particular cosmic scream, protected by distance, protected by time, and, most importantly, protected by the fundamental silence of space itself. Which brings us to an important realization. The silence isn't just absence, it's protection. We've spent considerable time exploring a hypothetical universe where sound can travel through space, and we've discovered that such a universe would be acoustically violent to a degree that makes our actual cosmos seem peaceful by comparison. Now it's time to return to reality and appreciate why the silence we take for granted is actually a form of protection. Earth sits in what might charitably be called a dangerous neighbourhood, cosmically speaking. We orbit a star that occasionally erupts with solar flares, releasing energy equivalent to billions of nuclear bombs. We live in a galaxy containing perhaps 100 billion stars, many of which will eventually explode as supernovae. Within our galaxy, at this very moment, massive stars are collapsing, neutron stars are colliding, and black holes are consuming matter, with releases of energy that dwarf our sun's entire lifetime output. And yet, we're safe, not just from acoustic violence, which can't reach us through vacuum, but from most forms of cosmic violence, thanks to a thin shell of gas we call the atmosphere. Earth's atmosphere is, by cosmic standards, almost absurdly thin. It extends upward from the surface for roughly 100 kilometers before fading into the vacuum of space. The entire mass of the atmosphere is about 5 times 10 to the power of 18 kilograms, roughly 1/millionth of Earth's total mass. If Earth were an apple, the atmosphere would be thinner than the skin. This thin shell might seem fragile, and in some ways it is. A sufficiently large impact could strip portions of it away. A nearby supernova could damage the ozone layer. A gamma-ray burst pointed directly at us could ionize significant fractions of atmospheric molecules. But for everyday purposes, and even for most cosmic purposes, the atmosphere is remarkably effective at protection. It absorbs harmful ultraviolet radiation from the sun, preventing it from sterilizing the surface. It burns up most meteors before they reach the ground, converting potential impactors into pretty streaks of light. It scatters and absorbs X-rays and gamma rays from distant cosmic sources, reducing them to harmless levels by the time they reach the surface. And crucially for our discussion, it dampens and dissipates acoustic energy. When violent events occur on Earth, volcanic eruptions, nuclear explosions, meteor impacts, they produce intense pressure waves. But these waves lose energy as they travel. The air absorbs acoustic energy, converting it to heat through friction and viscosity. High-frequency components are absorbed more readily than low frequencies, which is why distant sounds seem deeper. The treble has been filtered out by passage through atmosphere. Over distance, even the loudest sounds fade. The 1883 Krakatoa eruption, as violent as it was only audible out to about 4,800 kilometers, roughly 1/3 of Earth's circumference. The pressure waves circled the planet multiple times, but each time around it weakened. By the 4th or 5th circuit, it was detectable only on sensitive barometric instruments. The acoustic energy had been absorbed by the atmosphere, converted to slight heating of air molecules, dispersed into random thermal motion. This energy dissipation is crucial. It means that even catastrophic events remain localized acoustically. A volcanic eruption in Indonesia doesn't destroy cities in Europe through sound alone. A nuclear test in one country doesn't rupture eardrums in neighboring countries. The acoustic violence, however intense at its source, fades over distance into silence. In our hypothetical sound-carrying universe, this protection would be even more important. Without atmospheric dissipation of acoustic energy from cosmic events, pressure waves would propagate unimpeded until they encountered planets. And when they did encounter planets, when a supernova's acoustic shockwave traveling for decades finally reached an inhabited world, the results would be catastrophic. But in our universe, space is silent. The violence of the cosmos is expressed through radiation and particles, both of which our atmosphere helps protect against. And even when radiation makes it through, as with visible light, which we need to see, it's gentle enough not to harm us under normal circumstances. Beyond the atmosphere, we have another form of protection: distance. The inverse square law is one of the most elegant principles in physics. It applies to light, to gravity, to radiation, and, in our hypothetical universe, to sound. Double the distance from a source, and the intensity drops by a factor of 4. Triple the distance, and intensity drops by a factor of 9. The relationship is geometric, not linear, which means that modest increases in distance produce dramatic decreases in intensity. This is why we're safe from most cosmic violence. Earth is fortunately located far from most of it. The nearest star, Proxima Centauri, is 4.24 light-years away. Far enough that even if it exploded as a supernova, which it won't, being too small, we would be safe from most effects. The light and radiation would be spectacular, but not lethal. We'd see a brilliant new star in our sky, bright enough to be visible during the day, gradually fading over months. But we wouldn't experience catastrophic radiation doses. Distance protects us. The nearest likely supernova candidate, Betelgeuse, is roughly 500 light-years away. When it explodes, possibly within the next 1,000,000 years, possibly not for another 1,000,000 years beyond that, it will briefly become one of the brightest stars in our sky. It might cast shadows at night. It will certainly be spectacular, but it will not harm us. 500 light-years is far enough that the radiation, though intense, will be diluted to safe levels by the time it reaches Earth. Gamma-ray bursts are more dangerous because they concentrate energy into beams, but the odds of a nearby gamma-ray burst pointing directly at Earth are reassuringly low. Astronomers estimate that for Earth to experience a catastrophic gamma-ray burst impact, one would need to occur within about 5,000 light-years and point its jet directly at us. Within 5,000 light-years of Earth, we might expect a gamma-ray burst every few 100,000,000 years. Not impossible over geological time. Some mass extinctions in Earth's history might have been triggered or contributed to by gamma-ray bursts, but rare on human timescales. And even then we would face gamma radiation, not sound. The radiation would strip some of our ozone layer, increase surface ultraviolet levels, and potentially cause ecological disruption. It might trigger a mass extinction, but it wouldn't produce the instant, total obliteration that an acoustic wave at equivalent energy would cause in our hypothetical sound-carrying universe. Space's silence protects us in a way that distance alone might not. Cosmic violence remains localized mechanically, even when it propagates electromagnetically. A supernova destroys its immediate neighborhood through direct pressure and heat, but leaves distant systems untouched acoustically. The shockwave of stellar debris expands outward at thousands of kilometers per second, but it's not sound. It's actual matter moving through space, and it dissipates with distance as particles spread apart and slow down. This brings us to an important realization. The silence of space isn't an absence to be regretted. It's a feature, not a bug. It's part of what makes the universe habitable. If space were filled with even a moderately dense medium capable of carrying sound, the acoustic environment would be intolerable. Every energetic process would generate noise. Stars would roar continuously. Our own sun would produce a drone loud enough to be uncomfortable anywhere in the inner solar system. Every solar flare would send pressure pulses through the medium, battering planetary atmospheres. Every nearby supernova would produce acoustic shock waves that would strip atmospheres and heat planetary surfaces. Planets orbiting close to their stars would experience constant acoustic bombardment. The star's convection, its flares, its oscillations, all would produce sound that would batter the planet's atmosphere continuously. Over billions of years, this acoustic energy might erode atmospheres entirely, leaving worlds airless and dead. In dense stellar environments like globular clusters or galactic cores, where stars are packed thousands of times more densely than in our solar neighborhood, the acoustic chaos would be even worse. Multiple nearby sources would produce overlapping pressure waves, creating a turbulent acoustic environment where the interstellar medium itself never rests. Life trying to develop in such regions would need to evolve acoustic tolerance or shelter deep underground, where matter and distance could absorb the worst of the sound. And then there are the catastrophic events. In our silent universe, supernovae and gamma-ray bursts are dangerous primarily because of radiation. Radiation travels at light speed, arrives without warning, but can be shielded against with sufficient atmosphere or rock. It's a sharp, brief insult, intense but localized in time. In a sound-carrying universe, these events would also produce acoustic shock waves that arrive more slowly but carry devastating mechanical energy. A supernova's acoustic wave might take years to reach a neighboring star system, but when it arrived, it would carry enough energy to strip planets, crush moons, and kill any life present. The radiation would be the quick death. The sound would be the slow-motion apocalypse, approaching at the speed of sound, giving years of warning but no possibility of defense. The silence of space is thus a form of protection, a barrier that prevents mechanical energy from propagating between star systems. Violent events remain localized. A supernova destroys its immediate neighborhood, but leaves distant systems untouched acoustically. This localization is essential for the development of life. Earth has existed for 4.5 billion years, and life has existed for at least 3.5 billion of those years. During that time, countless supernovae have exploded within our galaxy. Dozens, perhaps hundreds, may have occurred within 1,000 light-years of Earth. We survive them all. We receive their light, sometimes brightening our sky with new stars that faded over months. We receive their heavy elements, forged in stellar cores and scattered across space to eventually become part of new planets and new life. But we never received their violence in mechanical form. The vacuum of space kept their acoustic energy at bay, allowing us to benefit from their chemical legacy without being destroyed by their physical power. The silence isn't empty, it's full of protection, full of separation, full of the gentle absence that makes presence possible. There's a lesson here about the nature of existence. We often think of emptiness as lack, as something to be filled, but sometimes emptiness is precisely what's needed. Just as the space between notes creates music, and the space between words creates meaning, the silence between stars creates the possibility of life. In a universe that allowed sound to propagate, life might still emerge. Evolution is remarkably persistent, but it would face an additional challenge, surviving not just the radiation of cosmic events, but their acoustic aftershocks. Perhaps life would evolve on worlds far from any stars except their own suns, in the quiet outskirts of galaxies, where supernovae are rare. Perhaps organisms would evolve to live deep underground, shielded by kilometers of rock from acoustic violence above. Or perhaps life would be rarer still, emerging only during quiet periods between nearby supernovae, only to be repeatedly extinguished when the acoustic storms returned. We don't know, we can't know, because our universe is silent. But we can appreciate that silence, not as an absence of something wonderful, but as the presence of something essential. The quiet of space is part of what allows planets to orbit stars peacefully. It's part of what permits atmospheres to remain bound. It's part of what enables consciousness to develop and wonder about existence. When you look up at the night sky and see the peaceful stars, You're seeing a universe that has chosen silence over sound, vacuum over medium, and in that choice lies our safety. The most violent events imaginable occur beyond our reach, their mechanical energy unable to propagate across the void, their destruction limited to their immediate neighborhoods. The universe is vast, violent, and indifferent, but it's also, by virtue of its fundamental structure, arranged in a way that protects us from its own violence. The vacuum is our shield, the silence is our blessing. There's something uniquely terrifying about space in human imagination, and it's worth examining why before we drift towards sleep. It's not just the danger. Plenty of environments on Earth are deadly, but the particular flavor of that danger. Space horror taps into primal fears that our species evolved over millions of years. Fears that become strangely amplified when projected onto cosmic scales. The first element is vastness. Humans evolved in environments where everything meaningful was within walking distance. A day's journey might cover 30 kilometers. A lifetime of exploration might encompass a territory a few hundred kilometers across. Our brains are calibrated for this scale. We understand distances we can walk, territories we can map, spaces we can conceptually hold in our minds. Space violates this calibration completely. The nearest star is 40 trillion kilometers away. The galaxy is 1,000,000 trillion kilometers across. The observable universe extends for 880 billion trillion kilometers. These numbers don't just exceed our intuitions, they shatter them. We can write them down, we can calculate with them, but we can't really feel what they mean. When we contemplate the universe's size, we confront our own insignificance in a way that's both humbling and terrifying. We're not just small, we're incomprehensibly tiny. A mote of dust in an ocean of void. The entire history of human civilization, all our wars and loves and discoveries and art, occurs on a planet that wouldn't be visible from even modest cosmic distances. We could vanish entirely, and the universe would continue exactly as before, unmarked and uninterested. This realization can provoke existential dread. If we're this small, this insignificant, does anything we do matter? The question is uncomfortable enough that many people prefer not to ask it. The second element is silence. Our ancestors evolved in an acoustic world where sound provided crucial information about threats and opportunities. The crack of a twig meant a predator approaching. The rustle of leaves meant prey moving. The absence of sound, true silence, was rare and often meant danger. Birds stop singing when predators are near. Forests go quiet before storms. Silence in our evolutionary history was a warning. Space takes this silence and makes it absolute. There's no sound because there's no medium to carry it. The violence occurring all around us, stars exploding, black holes feeding, galaxies colliding, happens in perfect quiet. Our brains find this deeply unsettling. We expect violence to be loud. We expect to hear danger approaching. Space denies us this, presenting a cosmos where catastrophe arrives silently, at the speed of light, giving no acoustic warning. It's the cosmic equivalent of a predator that makes no sound, and we're evolved to find that terrifying. The third element is helplessness. On Earth, we can prepare for danger. We build shelters against storms, weapons against predators, vaccines against disease. We're not helpless. We're clever apes who figured out how to protect ourselves from most threats our planet can throw at us. But against cosmic violence, what shelter protects against a gamma-ray burst? What weapon deters a black hole? What medicine cures exposure to vacuum? We can't fight cosmic threats, can't flee from them in any meaningful sense, can't prepare defenses that would actually matter if the universe decided to notice us. We are passengers on a planet we don't control. orbiting a star we didn't choose, in a galaxy whose motions we cannot influence. If the universe wanted to kill us, if a nearby star exploded, if our solar system drifted through a dense molecular cloud, if a rogue planet's gravity disturbed the Oort cloud and sent comets raining inward, we would face the consequences with no real ability to prevent them. This helplessness is terrifying at a deep level. We're a species that prizes control, that builds civilizations on the assumption we can shape our environment to our needs. Space reminds us that this control is local, temporary, and ultimately illusory. We're not the masters of anything beyond our immediate surroundings. These three elements, vastness, silence, and helplessness, combine to create space horror. They tap into fears that our ancestors knew, but amplify them to cosmic proportions. The result is a particular flavor of dread that's both primal and philosophical. And yet, here's where the paradox emerges. The very things that make space terrifying in imagination, its vastness, its silence, its indifference, are also what make it comforting in reality. Consider vastness again. Yes, it makes us insignificant, but that insignificance also means freedom. The universe doesn't care what we do. There's no cosmic judge evaluating our choices, no universal standard we're failing to meet. We're free to exist without the weight of cosmic significance pressing down on us. Our lives matter to us, to each other, to the small sphere of existence we actually inhabit. And that's enough. The vastness that makes us small also gives us permission to simply be, without needing to justify our existence to an indifferent cosmos. The distances that separate us from cosmic violence also protect us. That vastness is a buffer, isolating us from dangers that would otherwise be immediate neighbours. A supernova that destroys everything within 10 light years is still no threat to anything beyond 100 light years. The void is both a reminder of our insignificance and a shield that keeps us safe. Consider silence. Yes, it's eerie. Yes, it denies us the acoustic warnings we're evolved to expect. But that silence also means we're not bombarded by acoustic chaos. We don't have to constantly shield ourselves from pressure waves emanating from the sun. Our planet can orbit quietly, receiving gentle sunlight and nothing more violent than occasional solar flares, which our atmosphere and magnetic field handle gracefully. The silence of space, rather than being an absence to fear, is actually a blessing. It's part of what makes the universe habitable. In a sound-carrying cosmos, we would face constant acoustic bombardment from every energetic process in our stellar neighborhood. The quiet we have, the deep, fundamental silence beyond our atmosphere, is a form of protection we rarely appreciate because we've never experienced the alternative. Consider helplessness. Yes, we can't control cosmic events. Yes, we're vulnerable to dangers we can't prevent. But the universe's indifference also means it's not malevolent. It's not out to get us. Space isn't hostile. It's simply unconcerned. The asteroid that might someday threaten Earth isn't vengeful or evil. It's just matter following orbital mechanics. The star that might eventually explode near us isn't angry. It's just following the physics of stellar evolution. This indifference is liberating. We don't have to appease the cosmos. We don't have to perform rituals to prevent cosmic punishment. We're free to exist in a universe that has no agenda regarding us. The helplessness that seems terrifying is actually a kind of freedom. Freedom from cosmic judgment, from universal obligation, from the burden of mattering to anything beyond our own small sphere. When you watch the stars on a clear night, you're seeing a universe that is, for all its violence, somehow arranged in a way that allows you to exist. The silence of space is part of that arrangement. The void between stars is part of that arrangement. The vast distances that separate us from danger are part of that arrangement. This realization can shift cosmic horror into cosmic peace. The universe is immense, and we are tiny, but that immensity has room for us. The universe is violent, but that violence is happening far away, and we're sheltered. The universe is indifferent, but that indifference means we're free. We're not significant in the grand scheme, but significance is a human concept anyway. By human standards, the only standards that matter to humans, we're quite significant indeed. To ourselves, to each other, to the small blue planet that's our home. The stars aren't just distant furnaces awaiting death. They're also suns around which other planets might orbit, where other life might emerge, where other consciousnesses might look up at their night sky and wonder just as we do about their place in the cosmos. The void isn't just empty space to cross. It's also the peaceful backdrop against which beauty emerges, the silence that makes sound possible, the absence that defines presence. The universe has created conditions where matter can become aware of itself, where atoms forged in stellar cores can assemble into organisms capable of contemplating their own existence, where consciousness can emerge and ask questions about meaning and purpose and significance. That's remarkable. Not because the universe intended it. It didn't. It has no intentions. But because it happened anyway. Through nothing but physical law playing out over billions of years, the cosmos has produced observers capable of understanding the cosmos. We are the universe examining itself, and the fact that we're small doesn't diminish this. If anything, it makes it more extraordinary. Against all odds, in a vast and violent cosmos, on an unremarkable planet orbiting an average star, matter has become conscious. And that consciousness, right now, is preparing to rest, to surrender awareness temporarily, to drift into sleep, to dream whatever dreams come. And you can do so knowing that the universe, for all its vastness, for all its violence, for all its indifference, is arranged in a way that keeps you safe. The loudest sound in the universe would instantly kill you, but you'll never hear it. The universe has seen to that, not through care or intention, but through the simple physics of vacuum and the absence of a sound-carrying medium. And there's something deeply comforting in this realization that the cosmos, for all its violence, is structured in a way that keeps mechanical chaos contained, that catastrophic sound forever beyond our ears, that we can exist in peace while violence unfolds in silence, distant and harmless. We've travelled far tonight, from the silence of space to hypothetical cosmic screams and back to silence again. We've contemplated violence on scales that dwarf comprehension and understood why that violence cannot reach us acoustically. And now we come back to Earth, back to the quiet room where you're resting. The stars are still shining silently above you. GRB 080916 sees light reached us in 2008, carrying news of ancient violence across 12 billion light years, but it made no sound. It never did. It never could. The universe continues as it always has, vast, violent, and perfectly, protectively silent. If you've enjoyed this journey into hypothetical destruction and real safety tonight, if these explorations help you appreciate the gentle physics that keeps us protected, don't forget to subscribe to the Sleepy Astronomer. There are more cosmic mysteries to explore together, more paradoxes to contemplate, more reasons to appreciate the universe we actually inhabit. And if this particular meditation on silence and violence resonated with you, a like helps others discover these late-night wanderings through space and sound. Thank you for exploring the loudest sound that will never be heard, for understanding both cosmic violence and cosmic protection, This is the sleepy astronomer, wishing you clear skies, peaceful dreams, and the quiet comfort of living in a universe where the void itself keeps you safe. Good night and sleep well in the silence.